Alright, so we're going to take a look at section 14.2, area of polygons and circles. So first of all, if you recall from the last section, one of the things I want you to think about is whenever we're doing linear measure, which was our last section, if you recall, we said that linear measure is always one-dimensional, or it's first degree. And so usually when we think of this, we can think of just how long something is, just one dimension. Well, now we're going to be taking a look at area. And area models, or area measure, is always two dimensions. So oftentimes students will think of length and width. But so we have two of them. It covers a region. Like an area rug covers the floor in which you're standing on. Okay, so it covers a region. All right, so the first thing we want to do, sometimes with students it's easiest to see a visual model first. So what I did was, I have two examples here. And instead of taking the time to create a little dot board or geo board, you'll notice I have a first equation, or first figure rather, in blue, and the second one in purple. And we just have a regular dot board, or geo board, and rubber bands. And so what we can do is we can visualize shapes that are familiar. And so if we look at example number 1, and we want to find the area of the region, we want to figure out how much space it covers. And so what we can do is break this down into shapes that might be easier for students to see. And there's a lot of ways. So this first way I'm going to do this is I'm going to do using addition. Okay, so I'm going to addition of familiar shapes. And those shapes, remember, could be polygons or it could be circles, because those are what we've used so far. So what I'm going to do is I'm going to subdivide this. So I might, as a student, go, okay, I recognize a couple of things going on here. I recognize that if I put a line right here, and I call this, for the moment, region 1, and I do the same thing, and I'm going to break this down very small to begin with. I might see that I have 5 different regions that I could add together. And when I taught junior high and we would do areas, I would have them literally write it out. So we're going to write out regions 1 plus 2 plus 3 plus 4 plus 5 equals our total shape. And the reason I'm doing that is it gives them small pieces to analyze. So what is region 1? Well, region 1 is a square. Region 2 is a square. Region 3 is a square or a rectangle. You could do this using squares or rectangles. And then region 5 is a triangle. So when I'm first going over it with them, I would ask them, okay, how do you find the area of a square? And I would have them write it out. Base times height. Base times height. Or you could say side times side. But of course, a square is a rectangle, so I could write this out 4 times, and then for a triangle, it's half base times height. So then if we look at our regions, well, our base, it looks like this is 1 unit long by 1 unit long. Similarly, the same thing with the other squares. So the first time through, I would have the students, of course, fill in the base and the height for each of those 4 shapes. And then when we get to the triangle, you'll notice the base of the triangle is 1 unit long, and the height of the triangle also is 1 unit long. So I would have base times height. And as the shapes get more complicated, these numbers will change. But by breaking this down into regions that they can see and adding them all together, 1, 2, 3, 4 plus a half, we get 4.5 square units 4 units squared. Okay? Now that's do addition. What I'd like to do on the second example is instead of using addition, I'm actually going to use subtraction. I could, of course, do the exact same thing and break this down into common shapes and find the area of each one and add them together. But I could also use subtraction. Find the area. So you can, of course, try this one again. If you want a second example, try it again and break this into shapes. But this time, I want to use subtraction. So what do I mean? Well, in order to do subtraction, the first thing I'm going to do is I'm going to take a familiar polygon, like a rectangle, a square, a triangle, and I'm going to start with that region. So what I notice is, I notice the entire length of this region could be used if I consider this entire length, if I consider this entire width. So again, when I taught this in junior high, what I would tell them is, imagine you're making cookies, and you want the cookie to be the shape of that purple polygon. So think of cookie cutters. Usually you roll the dough out, and then you cut and take away the pieces you don't need. So in this case, I'm going to first start with the total region. And then I'm going to subtract out the parts that I don't need. In this case, I'm going to subtract out 1, 2, 3 pieces. So I'm going to subtract out region number 1, I'm going to subtract out region number 2, and I'm going to subtract out region number 3. And so we first begin with, okay, the shape of the original. If I did the entire shape, it looks like I have 1, 2, 3, 4, 1, 2, 3, 1, 2, 3. So it looks as though I have a rectangle. And I can really strongly recommend that when teaching this, have them first identify it using the actual words. Then I'm going to subtract out a triangle. I'm going to subtract out another triangle. And I'm going to subtract out a third triangle. How do you find the area of a rectangle? Well, the base and the height of that rectangle. Then you need the separate base and the height for each of these triangles. Triangle 1, triangle 2, triangle 3. All right, well, the base and the height. The base of this rectangle looks like it is 1, 2, 3, 4 by 1, 2, 3. So 4 units by 3 units. Then if I look at triangle number 1, its base and its height, it does not matter which one you call base and height as long as they are perpendicular to each other, which they are. So I'm going to call the base 2, and in this case the height happens to also be 2. For the second triangle, it's a little bit smaller, but it looks like the base and the height are 1 by 1. And for the third triangle, again, we have 2 by 2. So some of you may recognize right away that actually, according to my drawing, these two triangles are the same size. So I could have put them together and made their own square. But when in doubt, write it out. 2 times 2 is 4, half of that is 2, half of 1. 2 times 2 is 4, half of that is 2. And so I should end up with, let's see, 10, 8. I got a total of 7.5 square units for the shape of that purple region. Okay. Now, just out of curiosity, I might back that up and see if that's what I would get if I had done the addition method. So if I slide this over and use the addition method for number 2, I'm just curious if anybody already did that. Find area using addition. So if I break these in, I'm just going to do this a little quicker for and say, well, I have, let's see, I have a trapezoid right here. I have a triangle right here. I have another trapezoid right here, and I have a third trapezoid. So I'm just curious to see what I end up with if I do it using addition instead of subtraction. So I have a trapezoid for number 1. I have a trapezoid for number 2. Oops, I have 2 number 2s. I have a trapezoid for number 3. And I'm going to switch this one to number 4 as my triangle. So area of a trapezoid, 1/2 the height plus the sum of the bases that are parallel. 1/2 the height plus the sum of the bases, which are parallel. 1/2 the height plus the sum of the bases, which are parallel. And a triangle is half base times height. So for the first triangle, the height and the base, again, are always perpendicular. So I have 1/2 height of 1. One of our bases is 1 units. The other base is 2. For our second trapezoid, our height is 1. One of the bases is 2 units long. The other base is 3 units long. Our third trapezoid, the height is still 1. One of the bases is 1, 2, 3, and the other base is 2. And then for our triangle, our base and our height have to be perpendicular. So it looks like the base is 2 and the height is 1, or the other way around. So this gives us 1/2 of 3 plus 1/2 of 5 plus 1/2 of 5 plus 1/2 of 2. 3 halves plus 5 halves plus 5 halves plus 2 halves if I make the denominators the same. This gives me a total of 5, 10, 15 halves. 15 halves, or 15 divided by 2, is 7 1/2. So sure enough, whether I use the addition method, and there's many of ways to subdivide, you may have chosen rectangles and squares, we end up with the same result. So now let's practice looking at areas using both the English units and metric, and practicing with some other basic shapes. Oops, that slipped a little bit. Okay, we're still good. All right, so let's go back and practice some of our English units of measure and our metric. So just to refresh our memory, English units of measure. And we looked at a few of them a little while ago. Well, 14.1. I just dropped my protractor. We know that 12 inches is the same as 1 foot. We know that 3 feet is the same as 1 yard. And we know that 1,750 yards is the same as 1 mile. And 1,760 yards is the same as 5,280 feet. Okay. While I'm here, I'm going to go ahead and also we'll put down the metric conversion. That way we have them all here to just refer to. Oh, goodness. So our metric, if we remember our metric conversions, if we always are comparing in terms of our base unit, our metric units of measure, all right? So we have, first of all, just refresh our prefixes: kilo, hecta, deca. Then we have whatever our base unit is going to be. In our case, since we are using length, or we are talking about meters. If we're using, then we have deci, the prefix centi, and the smallest prefix is milli. So we had talked about one way to remember: King Henry died drinking chocolate milk. And so let's kind of refresh our memory here, and we should have that 1 meter is the same as, since I go 1 to the right, that's 10 decimeters. 1 meter, from meter, if I go 2 to the right, that's the same as 100 centimeters. If I go 3 to the right, it would be the same as 1,000 millimeters. But if I convert and go in the other direction, 1 meter is the same as 0.1 decameters. It is 1/100th of a hectometer, and it is 1/1000th of a kilometer, or a kilometer. So here's our metric conversions. Okay. And so let's practice a little bit. Same idea. We worked on how to practice in a linear manner, so we're going to do the same idea using area, or two-dimensional. So let's say I start first with an example such as, we're just going to practice conversions. Convert. So let's practice this. If I give you 1 square foot, so that would be 1 foot by 1 foot, or 1 foot squared. So imagine you have a tile or a shape that is 1 foot by 1 foot. Some of you may automatically have just done a conversion mentally and you figured it out. You may have mentally said, well, I know 1 foot is 12 inches, and I know 1 foot is 12 inches, and since that's a square, you already know what the answer is going to be, 12 by 12. But let's say we didn't think of that. So what I'm going to do is, let's convert it to inches squared using our conversion ratio. So start with what we know. We start with 1 foot squared. Well, what does that mean? Since it says feet squared, it literally means 1 foot times foot, because I have feet squared, which means I have 2 of them that I need to use our conversion rates on, or stoichiometry if you want to think about it from chemistry. I know our conversion fact. To eliminate one of these feet, I know that 1 foot is the same as 12 inches. And you'll notice that that will reduce one of these units of measure, but we need to do it again. So I'm going to do it again. 12 inches is the same as 1 foot. That's now going to reduce that unit of measure, and by multiplying horizontally, I end up with 12 inches times 12 inches, which is 144 square inches, or inches squared. Same thing you would have had if you had had this square or rectangle and you went base times height. So some might prefer picture, some of you might prefer using our units of measure and our conversion rates. So let's try this one. Same idea. 1 square yard, or yard square, is the same as how many feet square? So again, visually, I'm going 1 yard by 1 yard. 1 yard times 1 yard. So I have that rectangle, which is exactly the same as, I'm going to feet, 3 feet by 3 feet. So base times height is going to give us 9. So let's try it. If I start with yard squared, that literally means yard times yard. So I'm going to need the conversion rate twice. 1 yard is the same as 3 feet. 1 yard is the same as 3 feet. And now our yards will reduce. And sure enough, when we work that out, we are left with 3 feet times 3 feet, or 9 square feet, or feet squared. Okay. Does it always work? Absolutely. So, I may ask you to show me 2 ways how that would happen. So you could show the visual and you can show the arithmetic. All right, so let's try it with some of the metric. Let's say I have, for example, 1 square kilometer, and I want to change that to meters. So exactly the same thing. We could, of course, draw a picture. And I have 1 kilometer by 1 kilometer, which makes a square kilometer. And then convert each of those. Here I have a 1 by 1, and I could convert them each to meters. Meters is the same as, well, I want 1 kilometer, so I need to go the other direction. So 1 kilometer, I would need to move my decimal 1, 2, 3 to the right in order to make it into meters. Or I could do that as I go, which is what I'm going to choose to do. I'm going to start with 1 kilometer squared. 1 square kilometer is a kilometer times a kilometer. If I want to get rid of 1 kilometer and I want to know how many meters it is, I can start, of course, with my conversion facts here. I'm going to choose to use our little acronym, King Henry died drinking chocolate milk. And I'm starting with 1 kilometer, and I want to know how many meters that is. So I move my decimal 1, 2, 3 to the right to get to meters. So this would be 1, 2, 3 to the right, which makes it 1,000 meters. So again, 1,000 meters is the same as 1 kilometer. Now we have enough to reduce our units of kilometers. And we're left with 1,000 times 1,000, which is the same as 1 million meters squared. Got a couple more just to show you what happens when we switch between, because we may not always be going to meters, but we're going to do one more with meters. Let's say we have 1 centimeter squared, and again I want to go to how many meters squared is this. So I'm going to start off with my 1 always, when in doubt, write it out. Centimeters squared means I have centimeters times centimeters. I need to change everything to meters. So I need to convert centimeters to meters. And I need the centimeters in the denominator to reduce. So again, 1 centimeter is how many meters? Well, if I start here at 1 centimeter, and I need to go to meters, I need to move my decimal 1, 2 to the left. So this would become 1, 2 to the left, 1/100th. Also makes sense here. Now I can reduce. So 1/100th times 1/100th, okay, is 1/10,000th. So 0.0001 meters squared. Hopefully so far so good. All right. Well, let's say though we don't always want to go to our base units of meters or our base units of 1 foot, 1 yard. Let's see what happens if we practice with a couple that aren't just going to our base unit. We're not going to change anything because again, with mathematics, once you understand the concept, we apply the concept in each of the different situations. So let's say I asked you to convert, how about, let's do this one, 7 centimeters squared, but let's change it to millimeters squared. And of course we have to be talking about the same type of environment. So if I'm talking about area, it's going to convert to area. I cannot take area and convert it to linear. All right? So this time I'm going from centimeters to millimeters. So if I start with the 7, whoops, I forgot the centimeters. If I start with 7 centimeters, and centimeters squared means centimeters times centimeters, and this time I'm changing it to millimeters. So I'm going to reduce my centimeters, but I need to know how many millimeters. Since it is area, I need 2 of them. So 1 centimeter. And I'm going to do the same problem going the other direction, just to show you you don't always have to choose this, because some of you may be saying, why didn't we choose 1 millimeter? So we'll do the problem both ways. So in this case, let's see, 1 centimeter, I'm going from centi to milli. So I'm only going from centimeter to millimeter, 1 to the right. So if I take my decimal and I move 1 to the right, that would be 10 millimeters in every 1 centimeter. Now by reducing, I end up with 7 times 100, or 700 millimeters squared. I like to do it this way, then the millimeters are in the numerator already. If we had done the conversion fact the other way, well, let's see what happens. Actually, let's do this. Let's see what would happen if we set this up as 7 centimeters times centimeters. And we said, okay, I know I still need centimeters in the denominator to reduce, and I know I still need millimeters in the numerator to reduce. So I can see here that that's going to reduce out. But let's say instead you went, okay, I would rather go, how many centimeters are in 1 millimeter? So if I start at milli and I want to change it to centi, I'm going to move my decimal 1 to the left. So if I'm starting at 1 millimeter and I need to go 1 to the left, this would be 1/10 of a centimeter. So now when I reduce, I am literally left with 7 millimeter times millimeter. 1/10 times 1/10 is 1/100th. Or, for those that are doing this by hand, 1/100th. Dividing by a fraction is exactly the same as multiplying by its reciprocal. So you still end up with 700, or use your calculator, 7 divided by 1/100th still leaves us with 700 millimeters squared. So if you're reviewing decimals with a class, you could purposely set it up so that they're going to have to divide by a decimal. If you're reviewing fractions with a class, you could purposely set it up to where they're going to divide by a fraction, and dividing by a fraction is the same as multiplying by its reciprocal. All right. Now, I'm not going to go over every example that there is. There is a beautiful chart that's in your book that gives you these conversion factors along with acreage. And if you're measuring land mass, we talk about acre plots, or quarter of an acre plot, or half acre plot, or a hectare, okay? So I'm going to let you look up that conversion. So there's one more you want to definitely add with your English units, and that's going to be acres. So please make sure you add that into your notes. And now let's take a look at, well, some of these we have done. So we're going to kind of look at them again. Actually, I may have gotten a little ahead of myself a minute ago with the areas of trapezoid. But we're going to go ahead. I think we have these for now. If we come across an example, we'll just jot them down again. Okay, so let's take a look at area of parallelograms, area of triangles. And what's great is a parallelogram. If you recall, parallelogram has opposite sides parallel and congruent. So we may be talking about something that looks like what people often think of as a parallelogram. But remember, a rectangle is a parallelogram since opposite sides are parallel and congruent. A square is a parallelogram. So you have many different ways of looking at a parallelogram. And the area of a parallelogram is always the same. Area is always base times height, where the base is always perpendicular to the height. So it really doesn't matter which side you call base and height. Oftentimes we think of a rectangle, and we always say, oh, the base has to be on the bottom. Well, no, it doesn't. As long as we have a right angle, we can call this the base and the height, or you can do the other way around. I like to think of a square as a rectangle and just say, look, it's not a different formula. Since that's a right angle, it's still base times height, or side times side. With a parallelogram that is kind of pushed over, I guess I could have put a rhombus on here as well, because it's just a square that's been pushed over. So let's add the rhombus in here. Remember, rhombus, all four sides are the same. So with a rhombus, I have a base, and I would need to drop a perpendicular in order to call that the height. Okay? you can either put this height on the inside or the outside of the figure. So on the rhombus here, I'm going to put it on the outside. On this parallelogram, I'm going to drop it from the vertex, I'm going to put it on the inside. It does not matter. As long as the base and that height are the same, are perpendicular to each other rather. Okay, so let's look at a few examples and we'll practice some of these. All right, so let's say, for example, we give you a diagram and I tell you this parallelogram has one of these sides 8 centimeters, and it tells you the height on the inside. Make sure the units are the same. If they're not the same, you'll need to convert them. They always have to be the same unit. Area is base times height. So we have 8 centimeters times 3 centimeters, or 24 square centimeters, or centimeters squared. All right? Okay. So now let's say I give you one where perhaps I take a look at this picture. This is another one that looks kind of similar. And I give you that if I extend this side, this is still 8. And this time, however, I'm going to draw this altitude, which is also called the height, and I'm going to draw it looking this way. I can't really spin my whiteboard around, but you should see that they are at a perpendicular to each other. And I'm going to tell you that this is 4, and I'm going to tell you this other side is 9. So we analyze the shape. The shape is still a parallelogram. We're either given that, or I'll tell you it is by giving you all of these pieces of information. Opposite sides are parallel, opposite sides are congruent. So we know since it's a parallelogram, it's automatically base times height. So in this case, it's trying to determine which one's the base, which one's the height. They have to be perpendicular to each other. Therefore, in this case, the base and the height must be 4 and 9. So our base is 9 units, our height is 4 units. I did not give you any sort of measurement, so we just leave it as square units or units squared. All right. So the next shape we're going to take a look at are 2 other polygons we're going to take a look at that are the kite and the trapezoid. All right, so we have parallelogram. Let's take a look at the area of a kite. And you have that information on what a kite looks like from a previous chapter, but a kite has this sort of shape to it, and with a kite, the area of a kite is 1/2, because it does look as if you have a couple of triangles in there, diagonal 1 subscript times diagonal 2. And diagonals, just like they are with any other parallelogram, just goes from one vertex to the opposite vertex. So our diagonals, here I'll use pink again, our diagonals would go to opposite vertices. So here's a diagonal and here's a diagonal. And if you recall, diagonals of a kite intersect at a right angle. So those are the 2 diagonals. All right. And then the area of a trapezoid. And a trapezoid is a quadrilateral. It has 4 sides where opposite sides are parallel but not congruent. So if I have one section, oftentimes you think of a trapezoid as the other base. These are always parallel to each other, but they are not congruent. Or you could have, perhaps you have the parallel sides, and perhaps they have a right angle here, but you can see they're still parallel, but they're not congruent. All right, those parallel sides are what we call the bases. So this is a base, and this is a base, clearly not the same size. So usually we call one of them base 1 and the other one base 2. And then again, we need the height. The height and the base are always perpendicular. So I'll put the height, and on the other one that does not have a right angle already, you could either extend one angle, extend one side and make a right angle, or you could drop the height on the interior. That's just going to have to be depending on what they give you. And the area of a trapezoid is very similar to the area of a triangle. 1/2 base times height. But since we have 2 bases, we add them together. So the area of a trapezoid is similar to a triangle. 1/2 the sum of the 2 bases times the height. And oftentimes you see it written the other way around. But we know multiplication is commutative, so it does not matter which way we write it. So an example of a kite. Well, perhaps I give you a kite and I ask you for the area. So how much space it covers. And I'm just going to draw this picture, kind of roughing a sketch here. And I tell you that, let's see, let's make this diagonal, which always go to opposite vertices, 10 centimeters. And let's make the other diagonal, which go to opposite vertices. We'll make that entire distance 6 centimeters. Well, if I ask you for the area, we know the area is found by taking 1/2 the first diagonal times the second diagonal. 1/2 10 centimeters times 6 centimeters, which gives you 60 divided by 2, so 30 centimeters squared for area. And please make sure you include the units, because I need to make sure you have it as a 2-dimensional object since it's area. And then an example of a trapezoid. Let's take a look at, we'll draw one like one I didn't give you before. How about find the area. Let's have it go this way. This will be fun. Okay. So in this case, we have 8 meters by 5 meters, and let's give a height of 4 meters. Now some of you may have said height. The height looks like it's 8. No, the 2 sides that are parallel are called the bases. So in this case now, our area is 1/2 base times height, but since I have 2 bases, I add them together. So I get 1/2. The height would have to be 4 because the other 2 sides are the parallel sides, so we call those the bases. 5 meters plus 8 meters. Half of 4 is 2. 5 plus 8 is 13 meters. So we end up with an area of 26 meters squared. Okay. So now I want to move on to regular polygons. All right. So now let's take a look at if you have a regular polygon that's not a square, because a square we know is a parallelogram. So let's say you have, let's do it this way. Area of a regular, so all interior angles are the same, all side measures are the same length. So it's got to be regular, okay? Well, I'm going to try to draw something that looks somewhat regular. Let's say I give you this hexagon. It's a little off, but you can get the visual. And notice it always will fit within a circle where each of the vertices lie on the circle. So since each of the vertices lie on the circle, the distance from the center to each vertex would act as a radius. And notice we end up, again, we've done this before, we end up with a bunch of triangles. So the easiest way for me to do this is I think of this as 6 different triangles since it's a hexagon. And so we can still think of this as area. Well, we know how to find the area of one triangle. That's 1/2 base times height. And since we have 6 of them in this case, we would multiply it by 6. Okay? Now, this is not a triangle, so I don't really call this base times height. So you can think of this height, that height is what we call the apothem. Apothem is the height of one of those triangles. Okay, so we call the apothem A. So that's the apothem. And then this is just one of the sides. Okay, so the area, think of it again as a bunch of triangles. So we could think of it as the number of triangles that we have, 1/2 base times height. So 1/2, the base we're calling a side, and the height we're calling the apothem. But it's still 1/2 base times height times however many of them we have. So let's say, for example, I'm just going to give you a regular hexagon. So I'm going to try to draw it out again. It's a rough sketch. Each side is 8 units long. And all I'm going to tell you is the apothem is 5. So they might give you this distance from the center perpendicular to one of the sides. I told you it's 5. So again, if it's easier for you to think of this as a lot of triangles, I could subdivide this so it might be easier to visualize if I put this as a bunch of triangles. I apologize, that apothem is 5 there. Okay? Apothem is 5. So I'm going to think of it as area equals 1/2 the base times the height multiplied by how many sides there are, the number of sides. So area equals 1/2 the base, which we call the side, is 8. The apothem in this case is 5. And since it's a hexagon, the number of sides is 6. So we get 3 times 40, half of 6 is 3. So we get 120 square units. All right, and then the last shape that we're going to take a look at, we've seen before, but we're going to look at it again, is the area of a circle. The area of a circle area is pi times the radius squared. And it's easy to remember because we have to have square units, and so that's how it's different than circumference. If you recall, circumference only had radius to the first degree. Here we have radius to the second degree, or squared. So let's say I give you an example of, let's say I give you this example where I give you the diameter is 14 inches. Well, to find the area is always start with your given, pi r squared. Since we're given the diameter is 14 inches, well, the radius would be half of that because radius only goes halfway across, 7 inches. Therefore, we have pi times 7 inches squared. So the exact answer would be 49 pi inches squared. Or if they're asking you for a decimal value, here's your exact answer. Or if we use 3.14 since we're talking about measurement, we would end up with 153.86 inches squared if you use 3.14 for pi. Well, that's all the shapes. Now we can do some things with the shapes. So what I'm going to give you is what's called a sector. A sector is just part of a circle, like a slice of pizza. Think of it that way. Area of a sector. A sector, here's what a sector would look like. Here's a radius. Well, here's another radius. Since we're talking about area, we're talking about this entire region. So it's a sector, it's a slice. It's part of the circle. So again, I'm going to set it up like I did last section. Think of this as part of the area of a circle. Well, since it's part, it's a fraction of the area, pi r squared. And so just like we did before, in order to figure out that fraction, what fraction do we need? We need to know what piece out of the 360 degrees are we going to use. So we're going to use that central angle theta again. So what theta out of 360 are we going to use? So let's say, for example, I give you, how about we want a 40-degree wedge? So let's say we have this circle, and I tell you this central angle, mine's a little larger so you can see it, it's not drawn to scale. That central angle is 40 degrees. And let's keep the numbers nice. Let's give you a radius of 5 centimeters. So this is 5, this is 5. Well, now we just apply what we just learned. We know we only want part of the circle. So I need what part? I need 40 degrees out of 360. I want that part of the area, pi r squared. 40 out of 360, the degrees reduce, so I'm left with 1/9. The radius is 5 centimeters squared. I'm running out of room, so the exact area would be 5 squared is 25. 25 out of 9 pi centimeters squared. Which I believe, if I squeeze it in, I think it'll work. I think you can see this. which is approximately, if you can still see this on your board, 8.72 centimeters squared. Okay, so that's how we can find a sector. And then ultimately, if we want to create some shapes, this kind of cycles back around to how we started class. If we think about cookie cutter math, sometimes you may not have a geoboard or a dot plot, okay, dot paper. Maybe you have a picture. And so I know sometimes students get anxious when you see a picture, so we're just going to try to subdivide it and cut it up. So let's say I ask you to find the area of the last shape here. Find the area of this shape that is shaded. So the idea is thinking about cookie cutter math. How could you do this shape with cookie cutters? So I'm going to do the following. I'm going to draw the shape. You might see part of it by just the way I'm creating the drawing. And I am going to shade it in. Maybe we can see it better if I shade. I would like you to find the area. I don't want to touch the black part with the marker because it'll pick it up. But I'd like you to find the area of the pink shaded region. So one of the ways we can do this is, again, think cookie cutter math. Some of you will try to add the pieces. Others may try to subtract. So one area, if I add them up, I can clearly see I have a semicircle. I clearly have a sector, but the problem is we haven't talked about how to find this little region here. So instead, here's what I'm going to think. If I want the area of the shaded part, I'm going to do the following. I'm going to do the area of the entire circle. Okay. Then I'm going to subtract out the area of the triangle. It's as if I'm using a cookie cutter to take away the part I don't want. So we know how to find the area of a circle. We know the area of a circle is pi r squared. We know the area of a triangle is 1/2 base times height, where the base and the height are perpendicular. And so if I look at I'm going to tell you this is the center just to make it a little bit more obvious. In this case, the radius is 4, because the distance from the center of the circle out to a point on the circle is 4. So this would give me 16 pi. Now for the triangle, I need a base and a height. And we know the base and the height are always perpendicular to each other. So I can clearly see what the base is. The base is 4. Well, in this case, the height is also 4, because it too comes from the center of the circle to a point on the circle, so it's the radius. So both the radii are 4, which means both the base and the height are 4. So 1/2, 4 times 4, which is 16. So half of 16 is 8. So our exact answer would be 16 pi minus 8 units squared, or square units. Or if your directions say use 3.14 for pi, I believe when I did the calculation, somebody can always check, I got 42.24 square units. Okay? So there you go. That's part of our area, and I'll see you next time for 14.3.